Page 7 of Advanced Functions. A group of children attend a birthday party. The number of pieces of candy C that each child receives varies inversely with the number of children N. This is just a continuation of the problems that we were doing on the previous page. So first we're going to write that the candy varies inversely with the number of children, so the relationship looks like that. Now if we want to make an equation out of it, it will be C equals K over N. And then it gives us two numbers which are related to each other, which are 16 children and 10 pieces of candy. So that would be 16 would be N for children, and 10 pieces of candy. So what is the K value that corresponds to that? We would multiply both sides by 16, and so we would find out that the K value that makes this relationship true is 160. So then we're going to rewrite the equation with our K value inserted, which will be 160 divided by N. Now when there are 20 children, then we would put N equals 20, and then we would find out the number of the candy that's related to 20 children, which would be 160 divided by 20. Oops, 160 divided by 20, which is 8. We can also find that by putting the equation here, 160 divided by x instead of n. And then we look at the table. And then if we want to know what is the number of pieces of candy with 20 children, we look at x equals 20 and the y equals 8. Okay, let's go to 7. The variable y varies inversely with the square root of x. So the variable y varies inversely with the square root of x. And if we want to write it as an equation, it would be y equals k over square root of x. Then they give us a pair of numbers which makes that true, which is 3 equals k over square root of 16. And so that's equal to 3 equals k over 4. So if I multiply both sides by 4, I end up with k equals 12. And then if I want to write the equation that shows the relationship, it would be y equals 12 over the square root of x. So then it asks me, find the value of y when x equals 4. So then I just put x equals 4 in there. It'll be y equals 12 over square root of 4. Square root of 4 is 2, so that's equal to 12 over 2, which is equal to 6. So I'm going to just show you how that works. If I put it here, I'm going to put 12 divided by square root of x. Okay, there we go. And then I'm going to look at the table, and I'm going to look for the value of y when x equals 2, and I'm going to confirm, or 4, and I'm going to confirm that the y value is 6, and it is. Now I'm going to do part B. Find the value of x when y equals 3/2, which is 1.5. So I'm going to see if I can find the value of 1.5 here. 3/2 is 1.5, right? So if I can find 1.5. Getting close. There it is. So it's x equals 64. Okay, that's the one for that. If we were unable to find the exact y value here, we could get more precision by putting plus 0.1 or plus 0.01, and that would give us even more precision, right? Another way we could do it is we could graph y equals 3/2, so that's y equals 1.5, and then we could find the intersection of those two, right? And it looks like they're intersecting far to the right, so I'm going to change my window size so that the x max is 100, and then regraph it. And then I can see that they're intersecting here, and then I do second calc intersect to find their intersect. 5, hit enter 3 times. And the intersection is 64, 1.5, so x equals 64. So those are a few different ways to find the answer. Okay? 9H, optimization. Okay, an open top box is made from a piece of card measuring 8 by 6 with squares of side x centimeters cut out of the corners. Find an expression for the volume V of the open box in terms of x. Plot a graph of V against x. Find the x-intercepts. Find the local maximum and minimum values of V. Okay. So these are similar to some of the problems we did in optimization before. We did them where the resulting equation was a quadratic. And now we're going to do one where the resulting equation is a cubic function. Okay? I'm going to draw some pictures, and I'm going to do that on the next page because there's more space. Okay, so let me do the pictures here. Okay? So basically, what we're saying is we are going to take a piece of card, and the card is 8 centimeters by 6 centimeters. So we're going to have 8 by 6. And it says that we cut out a square from each corner. Okay? And this square is, it measures x by x. It doesn't really tell us how big the square actually is. Once we cut the squares out, then do you see how this makes a little pattern which you could have the edges fold up and it could become a box with no lid, right? So if we fold up the edges, it would look kind of like this, where the edges fold up. And if we connected all these edges here, we would end up with a box with no lid. Okay? Looks kind of like this. Okay. And let's say that this box has length, width, and height, and we want to figure out the volume of it. So the volume of a box is equal to length times width times height. Okay? So this is basically the answer. How do you find the volume? It's length times width times height. But they want only to have the variable x on the left side instead of L and W and H. So let's see if we can write L, W, and H as x, okay? First of all, if we label these edges, we can see that the height is equal to the edge of one of these cutout squares, right? This edge is this edge. So that length, we already know, we call it x. So we're going to replace H with x. What about L and W? L is this here, and W is this here. Well, we know that this whole thing is 8, and this smaller length is L. What is the difference between L and 8? Well, we know that L plus X is 8, right? So L plus 2X is equal to 8. So L is equal to 8 minus 2x, right? What about the width? The width is also related to 6 using x, because width plus x is equal to 6. So W is equal to 6 minus x, or 6 minus 2x. So we can replace W with 6 minus 2x. And we can replace L with 8 minus 2x. So our expression is going to be volume equals 8 minus 2x in parentheses times 6 minus 2x in parentheses times x. That's the expression for the volume. So let's graph that to see what it looks like. So into y equals, we're going to type x times parentheses x minus 2x times parentheses 6 minus 2x. And then we're going to graph that. And then we're going to adjust. We're going to adjust the zoom so that we'll use window. We'll adjust the zoom or the window until we can see the top of this curve. So let's say instead of 10, we'll put 100. Okay, that wasn't quite enough. And I think did I put it into X? Oh, I'm sorry. I didn't mean to put it in X. I meant to put it in Y. Graph. Okay, so we look at this curve and we see that there's a maximum and a minimum. There's some x-intercepts. The first thing that they asked us is, what are the x-intercepts? Okay, so the x-intercepts are, look like they're here and here. Let's look at the table and see if we can easily see the x-intercepts. Well, first of all, let me go back to the way the table used to be. And so I'm going to do second table set, 0, delta table 1. So that makes us go to the way table usually is. So, there's a 0 at 0. So one of the x-intercepts is 0. Another x-intercept is 3. And another x-intercept is 4. Because those are the three values of x which make y equal to 0. How could you find that on the graph? Remember, to find that on the graph, all you need to do is do second calc 0. So I could go second calc 0, which is number 2, and then we move the cursor so that it is slightly to the left of this intercept, and then we move it slightly to the right, and then we hit enter again. Guess, and we find out that one of the zeros is 3, 0, and we could find all of them using that method also. So now we know the x-intercepts. Let's find the maximum and the minimum, okay? So we'll do second calc maximum, and then we'll move the cursor slightly to the left of the maximum, and then we move it slightly to the right of the maximum, and then hit enter for guess. And the maximum is 1.13, 24.3. So I'm going to write that down. So the maximum is 1.13, 24.3. What about the minimum? The minimum is down there. I'll use second calc minimum, which is number 3. I move the left cursor slightly to the left of the minimum, and then I move the right cursor slightly to the right of the minimum, and I put in the guess. And the minimum is going to be 3.54, negative 3.52. Okay. I'm going to graph this because they asked us to graph it. And I think what I'm going to do is I'm going to graph from x equals 0 to, I don't know, x equals 6 or so. That would get me to about here. And then I'll graph from some negative values up until y equals 25 for sure, because that's higher than this maximum point. Okay? So I will put my axes, and I will put the x-axis here. And remember, let's see, I'm going to graph from 0 to 6 about. So that'd be 2, 3, 4, 5, 6. That's the x-axis. And the y-axis would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20, 25, and this would be negative 5. Remember that we have x-intercepts at 0, at 3, and at 4. The maximum point was 1.13, 24.3. So 1.13, 24.3, it would be about there. And the minimum value was 3.54, negative 3.52. So 3.54, negative 3.52. It's about there. So let me try to draw a smooth curve through these points. So there, there, and there, and then it goes up. Okay? So if I were to label these points, this would be the minimum, which was 3.54, negative 3.52. And the maximum is 1.13, 24.3. And so the y-axis refers to the volume, and the x-axis refers to the x value. Remember that the x value was being cut out of a card that was 8 by 6. What happens when x gets too big? So if x gets too big, you can see that the square is just getting bigger and bigger until you run out of card, right? So actually this square cannot be bigger than half of 6 or half of 8. So it really makes no sense to have an x value bigger than 3. Okay, so even though we graphed it bigger than 3, this is actually like the biggest you can physically get without running out of card. Okay, so that's kind of why the volume goes to 0 at this point. Okay, so between 0 and x equals 0 and x equals 3, the thing actually has a positive volume. Once you go past there, you get where you have a negative volume, which makes no sense anyway. Okay, and then, like, weirdly enough, when you go past 4, you actually start getting a positive volume again, but that's just a little trick. It's like 2 of the dimensions are negative. They multiply together to get a positive. In the real world, you basically don't have a box over here. Okay, so that's the way the graphing works. I'm not sure if we answered all the questions. Let's go back and look at the questions, make sure we answered them all. So, we plotted the graph. We found the x-intercepts. We found the expression in terms of x. State what the x-intercepts tell you about the possible ranges of values for x. So x basically should just vary from 0 to 3, right? Shouldn't be bigger than 3 because then the volume goes to 0 and you run out of card. Okay, 2, 3. E, find the local maximum minimum. We did that. F, explain why in real life V cannot be equal to one of the values we found in part E. So remember how it went up and it hit the maximum and then it went down and hit the minimum. The minimum, if you remember, was a negative volume. So no, it cannot be the minimum because that is a negative volume and you can't have a negative volume. Okay? Now if you look at the maximum, it was like 1.13 comma 24.3, right? What is the meaning of 1.13? What is the meaning of 24.3? 24.3 is the volume of the box at the maximum volume of the box by varying x. And 1.13 is the perfect value of x, which makes the volume exactly maximum. Okay, so that's what those mean. All right, let's do 9L and finish up this page. Given that x minus 6 equals x minus y equals 6, find the minimum value of xy. Okay, so let's say that our value is equal to xy, and we want to see when v is greatest. Now, we have the added constraint equation that x minus y equals 6. That's how we can make it so that only v is on the left and only x is on the right. We can replace y with an expression from this constraint equation. So let's solve for x, for example. That'll give us x equals 6 plus y, right? But I want something to replace y. So what I'm going to do is I'm going to solve for y. So that y value is equal to x minus 6. So I'm going to put x minus 6 in for y. So that'll give me x times x minus 6. Okay? Now I'm going to put that in the calculator and see what the minimum value of x times x minus 6 is. So I'm going to turn it on. I'm going to go to y equals, oops, didn't mean to do that. And then I'm going to put in the equation x times x minus 6. Okay. And then I'm going to graph it. And so the minimum value appears to be right there. Let's find out what it is by doing second calc minimum. So we'll do the left bound here, and then we'll move the cursor to the right side of the minimum over here. Hit enter, and then put in our guess, and the value is 3, negative 9, it looks like. So basically, when our x value is 3, our y value is negative 9, and that would be the minimum value of xy. Okay, just to not, I didn't mean to confuse, but like this y here, even though the y is the output value, this, in our case, y is actually v, right? Because once we put this in the calculator, this becomes big X, right? Big X. This becomes big X minus 6, and this becomes big Y, right? And so actually, our values here are big X and big Y, which correspond to little x and v. Okay, so this is x and this is v. So our smallest v value is negative 9. Let me just make sure it is by doing second table, because I couldn't really read that very well in the calculator. Yeah, 3, negative 9. Okay, so the minimum value, the answer is negative 9. That's it for this page.